In this part of the Computational Intelligence course related to fuzzy systems, we will start to fuzzy controller. We will examine the Cartpole problem as an example, in which the aim is to balance an upright standing pole by moving its foot. We will continue with fuzzy partitioning for being able to represent linguistic rules, and then we will examine the fuzzy rules and fuzzy partitioning for the Cartpole problem. Fuzzy control is the most successful application area of fuzzy systems, currently used in industry. It's a special kind of nonlinear table-based control method. Definition of nonlinear transition function can be made without specifying each entry individually. Examples are technical systems such as electrical engine moving an elevator or heating installation. The goal is to define certain behavior. For example, for the elevator, the engine should maintain certain number of revolutions per minute. Or for the heating installation, heating should guarantee certain room temperature. Control systems all share a time-dependent output variable. For example, revolutions per minute or room temperature. Output is controlled by control variable, for example, adjustment of current or thermostat. Also, disturbance variables influence output, for example, load of the elevator, or outside temperature, or sunshine through a window. Computation of actual value incorporates both control variable measurements of current output variable epsilon and change of output variable, that is delta epsilon, which is equal to d epsilon dt. If epsilon is given in finite time intervals, then set delta epsilon at tn plus 1 is equal to epsilon tn plus 1 minus epsilon tn. In this case, measurement of delta epsilon not necessary. As an example, we are going to consider Cartpole problem. It requires to balance an upright standing pole by moving its foot. Lower end of pole can be moved unrestrained along horizontal axis as shown here. The mass of the foot is m, and also the mass of the head is m. The influence of mass of shaft itself is negligible. The length of the shaft is L. It is required to determine force F, which is the control variable, that is necessary to balance pole standing upright. We are designing this pole to stand at upright position. That is, measurement of following output variables are needed. Angle theta of pole in relation to vertical axis, this is theta, this is the vertical axis. Change of angle, that is triangular velocity, theta prime, which is derivative of theta with respect to time. Both should converge to 0. Angle should converge to 0, and the change of angle should converge to 0. So the pole will stand at this angle. The notation is as follows. Input variables are shown as epsilon 1 up to epsilon n, and the control variable as eta. The measurements used to determine actual value of eta. Eta may specify change of eta. The assumption is that epsilon I from 1 to n, is value of xi, and eta is element of the output space. We have to find a control function phi, which is a function from the Cartesian product of the input space to the output space. That is, from the tuple from x1 up to xn to y. Angle theta is element of first input space, which is the interval between -70 and +70. Theoretically, every angle velocity theta prime is possible. Extreme theta prime are artificially achievable. We assume that the speed of theta, that is derivative of theta, is between -45 degrees per second and +45 degrees per second. That is, we assume that theta prime, element of the second input space, is element of the interval -45 degrees per second and +45 degrees per second. We assume also that the absolute value of force, shown as here, is less than equal to 10 Newton. So we are defining F, element of the output space, and which is in the interval -10 Newton and +10 Newton. The differential equations of the Cartpole problem, describing the dynamic of the Cartpole, it is given here. M, the mass of the food, plus M, mass of the head, multiplied by sinus square theta. Theta is the angle of the rod and vertical axis, multiplied by L. L is the length of the pole, and the second derivative of theta, plus M multiplied by L multiplied by sinus theta, cosinus theta, multiplied by the first derivative of theta square, minus M plus M multiplied by G multiplied by sinus theta is equal to minus F multiplied by cosine theta. Compute F at time t such that theta t and the derivative of theta t converge towards zero quickly. However, physical analysis demands knowledge about physical process. It is often very difficult or even impossible to specify accurate mathematical model. Description with differential equations is very complex. Profound physical knowledge from engineers is needed. Exact solution can be very difficult. It is not always necessary analytical solution. Instead of that, the control process may be developed without physical mathematical model. For example, human being knows how to ride bike without knowing existence of differential equations. The fuzzy approach is that simulate behavior of human who knows how to control. That is, a knowledge-based analysis. Directly ask expert to perform analysis. Then expert specifies knowledge as linguistic rules. For example, for Cartpole problem, the expert may say, if theta is approximately 0 and theta prime is also approximately 0, then f has to be approximately 0 too. In fuzzy control, fuzzy partitioning is used to formulate set of linguistic rules. That is, we determine linguistic terms represented by fuzzy sets. They are defined on reference sets for inputs from x1 up to xn, and the reference set for the output y. These sets are partitioned into fuzzy sets. For this purpose, for each reference set shown here, for example, for x1, we define P1 distinct fuzzy sets with the membership functions mu1 up to mu P1 on the reference set 1. And this is done similarly for other reference sets. And we associate linguistic term for each set. Consider, for example, the reference set x1. This is corresponding to interval between a and b of the real line. Then the membership functions mu1 up to mu p1 on the reference set x1. These are element of the fuzzy sets defined on x1. And these are triangular functions. The triangular membership function around x0 with slope epsilon is defined from the interval AB to a value in the interval 0, 1 such that from x in this interval to a value between 0, 1 such that that value is 1 minus minimum of epsilon multiplied by the absolute value x minus x0 and 1. We are choosing the minimum of these two. And this is subtracted from 1. For these membership functions from 1 up to P1 on the reference set x1 such that a is less than x1, where x1 is that center for the fuzzy set, and up to xp1, which is less than b, only for membership function 2 up to membership function p1 minus 1 on the reference set 1 are triangular. However, for the boundaries, the membership functions are treated differently. For the left one, left fuzzy set, the membership function 1 on the reference set 1 from interval a to b to interval 0, 1. The membership function is such that it is 1 if x is less than x1. So if x is less than x1, the value is 1. Otherwise, 1 minus minimum epsilon multiplied by x minus x1 and 1 is used. So it has such a shape. For the right fuzzy set, around xp1, so we are considering this fuzzy set, the membership function p1 for the reference set x1 is a function from interval ab to interval 0, 1 such that the value of the membership at point x is 1 if x is greater or equal to xp1, that is, if x is in this region, the value of the membership function is 1. Otherwise, that is, x is in this region, the value of the membership function is 1 minus minimum of epsilon multiplied by xp1 minus x and 1. So we have a line with slope epsilon. Here, the slope is minus epsilon. For example, consider a coarse partitioning. Here, the reference set is extending from minus 90 up to 90, and we have 3 fuzzy sets. The first one is called negative. It is around x1 and it has such a shape. The second fuzzy set called approximately 0. It is around 0. So x2 is corresponding to 0 and it has a triangular shape. And the last one is called positive. It is around x3 and this is the shape of the membership function for the fuzzy set positive. In this one, we have more fuzzy sets defined on the reference set. So this is a finer fuzzy partitioning. We have here seven fuzzy sets, which are negative big, negative medium, negative small, approximately 0, positive small, positive medium, and positive big. So we have such center points, and around those, the fuzzy membership functions are defined. Notice that only the leftmost one and the rightmost one have trapezoid shape, and all the others are triangular membership functions. Here we have 19 rules for the Cartpole problem. As an example, consider the Cartpole problem and assume that the reference set is partitioned into 7 fuzzy sets. Support of fuzzy sets are the intervals with length 1/4 of whole range of x1, similar fuzzy partitions for x2 and y. Notice that this is corresponding to angle theta, and this is corresponding to derivative of theta, and this is the output. The next step is specify rules in the form if epsilon 1 is something fuzzy set and the other specifications, and epsilon n is this is a fuzzy set, and then this is output eta is b is another fuzzy set. Here a1 up to an and b represent linguistic terms corresponding to membership functions from mu1 up to mu_n, and mu, this is for the output, according to reference sets x1 up to xn and y. The rule base consists of k rules. For the input variable theta, on the reference set from -90 up to +90, and also similar for the theta prime. The negative big, negative medium, negative small, approximately 0, positive small, positive medium, and positive big are defined as fuzzy sets, and also for theta prime. And here we have 19 rules, and these are saying that if theta is something, theta prime is something, then consider the corresponding intersection. Then this is defining what should be 4y. For example, consider this column and row. This is saying that if theta is approximately 0, if theta is approximately 0, and theta prime is negative medium, then f, the force is positive medium. The challenge is how to define function phi, which is mapping x to y that fits to rule set. The idea is that represent set of rules as fuzzy relation. Specify desired table-based controller by this fuzzy relation. Consider on the crisp sets, then solving control problem is equal to specifying control function. That is, phi is a function from the input space to the output. These are the control variables and these are the inputs of the controller. Phi corresponds to relation. It's a relation phi on x and pi x. For x, the value of the relation is pi x, such that x element of the reference set, and this relation is a subset of the x Cartesian product y. For measured input x, element x, the control value is the phi x, which is x composition, the relation